Section 5.4, we're going to learn to solve systems of equations using what's known as the eigenvalue method. All right, again, remember what we did back in Chapter 2. We had something like y double prime minus 4y prime minus 5y equals 0. How did we solve that equation? We created the characteristic polynomial. And where did that characteristic polynomial come from in the first place? Nope.
Good guess.
A good guess. That's exactly right. What we did,
I just had a good guess.
we made a guess that our answer looked like e to the RT. We took the derivative. We took the second derivative, and we plugged it all in. And when we plugged it all in, we ended up with r squared e to the RT minus 4r e to the RT minus 5 e to the RT equals 0. And then we went about solving that equation. First thing we did is we divided everything by e to the RT. And that's where our characteristic polynomial came from. We made a guess at what the answer was going to look like. We plugged it in, and we worked it out, and we saw that, hey, look at this. You got y double prime, 4y prime, 5y, and here you ended up with r squared minus 4r minus 5. The characteristic polynomial fell right out from the original equation. Then we factored, if we could, and that gave us our solution. Our solution was C1 e to the 5t plus C2 e to the negative t. All right, so now chapter 5, 5.4. We're going to have this system of equations maybe. x1 prime equals 2x1 plus 3x2. And then x2 prime equals 2x1 plus x2. We're going to write this as a matrix equation. As a matrix equation, this is what we just did for problem 13. X prime is going to equal what? 2, 3, 2, 1 times x. I'm going to take a guess at what my solution would have to look like. What's the solution have to look like? An answer x, what does it have to be? It's got to have an x1 and an x2. So it's got to have two functions, an x1 and an x2. So I'm going to guess that my answer has an e to the lambda t times some number a1 and some number a2.
That's very easy.
So it could be written as a1 e to the lambda t, a2 e to the lambda t. Now personally, I wish the book used r instead of lambda, because we used r up here when we made our guess. Why in chapter 5 did they decide to use lambda? Well, because that's the traditional technique lambda's used. Lambda's going to be called our eigenvalue. Okay, so this is quite often written as e to the lambda t times the vector v. a1, a2 is just the vector v. Well, if the vector x is e to the lambda t times vector v, then what would the vector x prime be?
Lambda
lambda e to the lambda t times vector v. Remember, vector v just contains numbers, a1 and a2. So we have a function.
So it just,
It's like a constant. We have a function times a constant. So when you take the derivative, the constant just stays.
left.
So you couldn't get that just from the other x prime? We have a vector x prime equals that matrix over there, and we have it again as the lambda.
Right, because what I'm going to do now is I'm going to take this x prime and I'm going to plug it in right there, and I'm going to take this x and I'm going to plug it in right there, and then I'm going to see if I can solve that equation. My goal is to figure out what does the number lambda have to be. Okay, so we have lambda e to the lambda t times vector v equals 2, 3.
Lambda equals that matrix.
What's that?
It just means lambda equals the matrix, right?
Well, lambda's a number, so lambda can't equal a matrix.
You would just divide by even the change.
Oh, well, yeah, in a minute here, and let me plug everything in. You're absolutely right. So when I plug in for x prime, I get lambda e to the lambda t times vector v. And then I plug in for vector x. Vector x is e to the lambda t times vector v. And you're absolutely right. I can take that equation and I can divide both sides by e to the lambda t. Max.
T is matrix.
Oh, t is an exponent there. Yes, sorry. T is an exponent there. Okay, so you're absolutely right. I can divide by e to the lambda t. I have lambda times vector v equals 2, 3, 2, 1 times vector v.
No, the reason we can't do vector v over is because it's technically a matrix.
Vector v is a matrix. I can't divide by a matrix. I can't take the inverse of this matrix, unfortunately. Why not? Because this matrix is a 1 by 2 matrix. In order to have an inverse of a matrix, the matrix has to be square. So I can't divide by matrix V. I also can't multiply both sides by matrix V inverse. What I can do is I can rewrite this as 0 equals 2, 3, 2, 1 times vector v minus lambda times vector v. Why would I do that? That's an excellent question. Why would I do that?
Make it homogeneous?
It did make it homogeneous, and more importantly, I can factor out a v. Okay? So when I factor out a v, I'm going to have 0 equals 2, 3, 2, 1 minus lambda times vector v. Okay, but now we have a new problem. I have a matrix here, 2, 3, 2, 1, and I'm trying to subtract a number. How do I take a matrix and subtract a number? That's right, you can't. Doesn't work. So when we factored out the vector v, we really don't just have lambda left here. What we have is lambda times what's known as the 2 by 2 identity matrix. What's the 2 by 2 identity matrix?
0, 1, 0, 1, 0, 0.
1, 0, 0, 1. So what we have is 2, 3, 2, 1 minus lambda times 1, 0, 0, 1.
Would you distribute lambda into that matrix?
Now I'm going to distribute lambda into that matrix, and then I can simplify. I can combine my matrices. So this becomes 2 minus lambda, 3, 2, 1 minus lambda, times vector v, and that has to be 0. Well, that's not it yet. When we get all done, what's our goal?
Lambda.
We want to figure out lambda, which will give us a solution to the equation. All right, now there's an important theorem from linear algebra that says this equation has a solution if and only if the determinant of this matrix is a special number. 0. So we need the determinant of this matrix to equal 0. How do I find the determinant of that matrix?
It's the 1 over.
You multiply that way. 2 minus lambda times 1 minus lambda minus, and you multiply the other way, 6 equals 0. Multiply these together, combine my like terms, I end up with lambda squared minus 2 lambda minus lambda is minus 3 lambda. And then when I distribute here, I'm going to have a 2, but then 2 minus 6 is minus 4 equals 0. So finally, we've gotten to what we wanted. What did we want? What's that thing called? There's how you get your characteristic polynomial.
Wow. And then you just simplify.
Now you can factor, now you can solve. So this is lambda minus 4, lambda plus 1 equals 0. So we end up with 2 eigenvalues. Those are called the eigenvalues. Which is good. It's good that we ended up with 2 eigenvalues. Why is that a good thing? Because we started with a 2 by 2 system, which means we needed to come up with 2 solutions.
So what happens when these have like complex answers?
That's an excellent question. We'll answer that in a little while here. What happens when these numbers turn out to be complex numbers?
You can't just stay away from them.
Well, we can just avoid them. No, that's unfortunate. Okay, so now we're not quite done yet, because remember what we had. We started with x being e to the lambda t. We figured out lambda, but then we assumed that there were 2 numbers here, a1 and a2. We also need to know what those 2 numbers are. Okay, so we're going to take this equation right here, and we're going to plug in our values for lambda. We're going to plug in 4. We're going to plug in negative 1.
Now, does it matter which one you go to?
Yeah, you got to do them both. Okay, so we're going to have for lambda equals 4. We plug into this equation. 2 minus 4 is negative 2. 3, 2, and negative 3. And that has to be some vector v. I'm just going to call this one a1, a2. Has to be 0, because this is equal to 0 over here. So that gives us a system of equations. 2 equations, 2 variables. But it is a 0 vector, yes. What can you tell me about that system of equations?
You can do the RAF without like 2.
I could, and how many answers am I going to get? More than 2. Infinite. This is a dependent system. Why is this a dependent system?
Scalable.
If I take the first equation, multiply by negative 1, I get the second equation. There are an infinite number of correct solutions. I need one of them. Any old answer that you like. If there's an infinite number of answers, you should be able to find one.
How much is 0? 0, 0.
I can't use 0, 0.
1.
I can't use 0, 0 because if I use 0, 0, then my solution is just going to be 0.
No.
That's no good. So I need any other answer. I should have been more specific.
So no trivial solution?
No trivial solutions. Well, let's look at this. If I multiply across and down, I get negative 2a1 plus 3a2 has to be 0, which says 3a2 has to be the same as 2a1. So tell me a number that you could plug in for a1 and a number that you could plug in for a2 and make that a true equation. a1 could be the number 3, and a2 could be the number 2, and then I would have 6 equals 6. All right, so there's my eigenvector. This is called. My eigenvector was 3, 2. All right, now I have to do the exact same thing for lambda equals negative 1. I go back up here, and I plug in negative 1. 2 minus negative 1 is 3. That's a 3. 2. 1 minus negative 1 is 2. Times, I'll call this one B1, B2, I guess. Has to be 0, 0. Once again, you get a dependent system of equations. There are an infinite number of correct answers. Give me one correct answer. 1?
For both.
For both. Close. If I plug 1 in, I'm going to have 3 times 1 plus 3 times 1 equals 0. 1 is 1 and the other one is negative 1. There's a correct eigenvector. Does it matter which one I make 1 and which one I make negative 1? No, for no particular reason I went that way. Okay, so here's our general solution. Our general solution is the vector x is, it's got c1 e to the 4t times our eigenvector 3, 2 plus c2 e to the negative t 1, negative 1. Or if you prefer, I ran out of room, so I'm going to write it up here. You could write your answer as x1 equals. What would x1 be? x1 would be the top row, and x2 is the bottom row. So x1 is 3c1 e to the 4t plus c2 e to the negative t, and x2 is 2c1 e to the 4t minus c2 e to the negative t. So you can either write your solution in vector form, or you can write your solution in system of equations form, whichever one you prefer.
So you don't care which one you do?
Nope, I don't care how you leave your answer. Okay, so that seems time-consuming. But once you get it, it becomes pretty quick. x1 prime equals 4x1 plus x2. You guys like to see, don't you?
Yeah.
Very fussy.
You could always just call in sick today, like everyone else.
x2 prime equals 6x1 minus x2.
Did your kids have school today? Or? No, that's not me.
Well, my kids are in school.
Like I was sticking out there too. That thing's crazy.
It is sticking a little bit on the ground, yeah.
It's what, April 23rd? No, it's like that goes right there.
All right, so x prime is 4, 1, 6, negative 1 times x. Okay, so this time I don't need to go through the whole derivation of how I got it. Where did my characteristic polynomial come from? We made a guess that x has to have the form e to the lambda t times vector v. But I did a whole bunch of work, and what it came down to is I needed
Lambda vector v.
the determinant of this matrix, 4, 1, 6, negative 1, minus lambda times 1, 0, 0, 1 to be 0. That's how you get your characteristic polynomial. It's your coefficient matrix minus lambda times your identity matrix.
Where's the v?
That's the determinant.
Where's what, Max?
The v.
Well, remember what happened all the way through here. We got to the point where eventually we factored out the vector v, and so we ended up with our characteristic, our coefficient matrix minus lambda times the identity polynomial. We will figure out the vectors v later. Once we have the eigenvalues, we'll figure out the vector v for each eigenvalue. Those will be our eigenvectors. The important thing is, for a system of equations, that's how you get your characteristic polynomial.
George, is it the determinant of that whole thing or determinant of 4, 1, 6 minus?
Determinant of the whole thing. So typically this is just written as determinant of 4 minus lambda, 1, 6, minus 1 minus lambda. Usually that's just done in one step right there. You just subtract lambda down the diagonal. Liam?
That's what I was going to ask.
Correct. So typically, once we write our equation in vector form, we jump immediately to this line. You simply take the determinant of the matrix where you subtract lambda down the diagonal. And that gives you your characteristic polynomial.
We solve for our lambda values.
Correct. We'll solve for our lambda values. Once we solve for our plug our lambda values in and solve for our eigenvectors v. Okay?
So are we ever going to do anything on a 2 by 2 matrix or 3 by 3, 2 by 3?
On a test, I would certainly not give you a 3 by 3. Why not?
Yeah.
Computing the determinant of a 3 by 3 matrix is time consuming. And unfortunately, you can't use your graphing calculator to compute the determinant because it has variables in it. So no, on a homework problem, you might get a 3 by 3. On a test question, you certainly would not get a 3 by 3. It simply would take too long. Okay? Okay, so we find the determinant. The determinant is 4 minus lambda times minus 1 minus lambda minus 6 equals 0. There's our characteristic polynomial. Distribute it. Lambda squared. And then I'm going to have a minus 4 lambda and a plus lambda, so that's minus 3 lambda. I've got a minus 4, but then I've got this minus 6, that makes a minus 10 equals 0. There's my characteristic polynomial. Can you factor that there, characteristic polynomial?
Yes.
Lambda minus 5, lambda plus 2 equals 0. We get two answers. Lambda equals 5, lambda equals negative 2. Now I plug them in separately, and I have to find a relationship to get my eigenvectors. All right, for lambda equals 5, I take 5, I plug it in here, I get negative 1, 1, 6, negative 6, times some vector a1, a2, has to be the 0 vector. When you get to this point, you should, if you've done everything correct, this should always give you a system of equations that has an infinite number of solutions. What if you get to a point where you have a system of equations that does not have an infinite number of solutions? You made a mistake, you got to go back up. You've got the wrong lambdas somehow. You made a mistake somewhere. Okay, so what's a solution for this equation?
1, 1.
1, 1 would work, because if these are both 1, when I multiply I would have negative 1 plus positive 1 equals 0. That would work. So our eigenvector here is 1, 1. Repeat, do the exact same thing for lambda equals negative 2. 4 minus negative 2, that's 6. 1, 6, 1. Clearly a dependent system because they're exactly the same. What's a solution for that system of equations? 1 and negative 6 would work. Because that would give us 6 plus negative 6, that's 0. Could I use negative 1 and positive 6? Absolutely, if I wanted to. Is there only one correct answer? No, in fact, I could use 2 and negative 12 if I wanted to. I could use negative 1/6 and 1. So there's a lot of different ways to write the answer here. Okay, so final solution is x equals, we're going to have C1 e to the lambda e to the 5t times 1, 1 plus C2 e to the negative 2t times 1, negative 6. Or if you prefer, x1 is C1 e to the 5t plus C2 e to the negative 2t, and x2 is C1 e to the 5t minus 6 C2 e to the negative 2t.
Are you ever going to give us initial values for C1 and C2?
You possibly may be given initial values so that you have to find C1 and C2, but that's really nothing new.
Right.
If I give you initial values, you're just going to plug in and solve the new system of equations. So yes, that may happen.
Okay.
Other questions? Greg?
What is the eigenvector?
This, there are two eigenvectors. For this eigenvalue lambda equals 5, the eigenvector is the vector 1, 1. For the eigenvalue lambda equals negative 2, the eigenvector is the vector 1, negative 6.
And x for last part, that's eigen what?
The last part?
Yeah.
Nothing, that's just the answer. No eigen in that word. Max.
So how does it get harder?
How does this get harder? Well, that comes along with Jesse's question. And Jesse's question was, what happens if you get complex solutions? Or, what was your...
Non-homogeneous.
If it's non-homogeneous, that gets harder too. Looking at the homework, there are no non-homogeneous problems.
Looking at the future test, are there any non-homogeneous problems?
If it's not in the homework, it won't be on the test.
Variable coefficients?
No.
No.
Remember, we had issues in chapter 2. What if we get lambda equals 5 and we get lambda equals 5 again? What if you have a repeated root?
Oh, that's not today.
That's not today, that's correct. That's covered in section 5.5 and we don't do that in this course.
All right.
So we won't deal with repeated roots, but let's deal with complex roots. So it gets a little bit harder when you have complex roots. Alright, so x1 prime equals x1 minus 5x2. And x2 prime equals x1 minus x2. x1 prime is x1 minus 5x2. x2 prime is x1 minus x2. Alright, I write it in vector form. X prime equals 1, negative 5, 1, negative 1 times x. I write down my characteristic polynomial. My characteristic polynomial is the determinant of the matrix 1 minus lambda, negative 5, 1, minus 1 minus lambda has to be 0. find the determinant. 1 minus lambda times minus 1 minus lambda plus 5 is 0. Multiply that all together, I have lambda squared. Then I'm going to have a minus lambda on the outside, a plus lambda on the inside, so those cancel out. A 1 times a negative 1, that's negative 1. Negative 1 plus 5 is 4, equals 0. Not plus or minus root 2.
No.
Getting closer. Plus or minus
2i.
2i. And equals plus or minus 2i. All right, so again, back in chapter 2, what did we see happened when you ended up with a complex solution? You ended up with sines and cosines. We're going to end up with sines and cosines here. Okay. Now, I've got to compute my eigenvector. So when lambda equals 2i, I'm going to have 1 minus 2i, negative 5, 1, negative 1 minus 2i, times my eigenvector a1, a2, has to be 0, 0. Assuming that I've done everything right, that should be a dependent system of equations, which means it should have an infinite number of correct solutions.
But they're all imaginary.
They are going to have imaginary answers in them too. Yes, they are. Greg?
You put it in the matrix, right? Put that in the matrix.
I could on my calculator if I put that in matrix. What my calculator is going to do is it's going to tell you that that's a non-invertible matrix. It's going to spit out an error. Calculator won't solve that because it has an infinite number of solutions.
It doesn't have time for that.
Doesn't have time.
Augment it with a 0?
What's that?
Even when you augment it with a 0 vector?
Even when you augment it with a 0 vector, it's going to give you an error that's a non-invertible matrix. Okay, so we're going to have 1 minus 2i times a1 minus 5 times a2 has to be 0. Give me a solution. What do you want for the number a1?
0.
Can't be 0. Can never use 0 for these. You can never have the 0 vector.
No.
I'm going to use the number 5 for a1. So if I use the number 5 for a1, first off, where did I get the number 5? It was that number right there. So what am I going to use for a2?
1.
Now, 1 minus 2i. Because if I put a 5 there and a 1 minus 2i there, I'm going to have 5 times 1 minus 2i minus 5 times 1 minus 2i. That'll definitely be 0. So there's my eigenvector. My eigenvector has complex numbers in it. Okay, so my answer is x is e to the 2i times 5, 1 minus 2i. But you might remember, what was e to the 2i? What happened when we took e and raised it to a complex number? We got cosine and sine. So this is cosine of 2t plus I sine of 2t. That was Euler's special formula there. And that's going to be multiplied by 5 and 1 minus 2i. That's the same as 5 cosine 2t plus 5I sine 2t. What have I done so far? I took this cosine 2t plus I sine 2t and multiplied by 5. Now I got to do the same thing. I got to take cosine 2t plus I sine 2t and multiply by 1 minus 2I. To do that, I've got to do FOIL, don't I? So I'm going to have cosine 2t minus 2I cosine 2t plus 5I sine 2t. And then for this last one, I'm going to have I times negative 2I. What's I times negative 2I? It's plus 2 because I squared is the number negative 1. So that becomes plus 2 sine 2t.
Yeah.
Here's my final answer. The final answer is x1 and x2. To write down x1, you're going to have the real portion, so you're going to have 5c1 cosine 2t plus the complex portion. The complex portion is plus 5c2 sine 2t. We absorb the I with the c2. c2 is just a constant, so c2 absorbs that I into it. I is just a constant also. And then we do the same thing for x2. x2, we're going to have the real parts. What are the real parts of x2? So we're going to have c1 times cosine 2t plus 2 sine 2t plus, and then we do the complex parts. That's going to be c2, 2 cosine 2t.
We didn't throw the I out, right?
Exactly, same trick. That c2 is absorbing the I, so you factor the I out of those two that have the complex part. Oops, I made a mistake. That has a minus in front of it. That should be a minus 2 right there.
We should never have to do this and then have given values for C1 and C2.
Actually, if I were to give you values for C1 and C2, solving would be quite easy. So let's say I gave you some initial conditions. x1 at 0 is 2, and x2 at 0 is negative 3. Why do I say this is quite easy? Well, take 0 and plug it in here. What happens when you plug 0 in? The sine is 0. The cosine is 1, so you end up with 2 equals 5c1.
That's if you only give us, at 0.
And I would always give you initial conditions starting at 0. Yeah. I'm such a nice guy. That's
Best
right.
teacher ever.
And then when I plug in 0 for the other one, I'm going to have negative 3 equals. When I plug 0 in, that one's going to be 0. That one's going to be 0. This one's going to be 1 times C1, but we already know C1 is 2/5. And then we would have a minus 2C2. So I'm going to have negative 3 minus 2/5. How much is negative 3 minus 2/5?
It's 17 over 5.
Negative 17 over 5, and then I have to divide it by negative 2. 17 over 10. Giving you initial conditions when you end up with complex solutions for your characteristic polynomial is actually easier than giving you initial conditions when you end up with real solutions.
It makes sense because the 0 is going to cause the sine, cosine,
The 0 causes the sines to disappear and causes the cosines to be 1.
which only
So you don't really end up with a system of equations. You end up with one equation with one variable. Where if I were to give you initial conditions here, you would end up with a C1 plus C2 equals something. you would end up with a C1 minus 6C2 equals something. You'd have a real system of equations that you would actually have to solve.
Matrix.
And you could use a matrix there, correct. So it's actually easier to have initial conditions when you have complex solutions for your eigenvalues.
Yeah.
So this is quick.
Little identity.
So, quick one, yep.
These kind of seem straight. I don't know, they're not the least scary thing. I think it sounds less.
I would agree. How we got to this point in the first problem was a little bit hard.
Yeah.
But once you recognize that every problem is going to work the same way, you simply write it down, you compute your characteristic polynomial, and from there it's just a matter of plugging numbers in. Pretty simple. I agree. Once you get to here, this process is pretty easy. And now that you know how to do it, you start right there. And you just move through. So I agree. As far as I'm concerned, this is by far the easiest technique for solving systems of equations. Other questions, comments, concerns?
Wait, so just to clarify, test is going to be Thursday up to what?
The test will cover sections 5.1 through 5.4 and 3.1 and 3.2. We will be finished with 3.2 by Monday.
Okay. Unless we get snowed out.
Unless we get snowed out, that's true.
This is happening.